difference on their volatility to concentrate the more volatile component in the vapor phase than in liquid phase on contact liquid and vapor phase. Raoult's law relates. You say this is for concentration in liquid and Dalton's law in vapor. Raoult's law relates the partial pressure of a component to its concentration in liquid at equilibrium. Pi is equal to Xi Pi. Pi is the partial pressure of component. Xi is the mole fraction of I in solution, and Pi is the vapor pressure of I at the same temperature. Now this is Dalton's law. Pi is equal to YIP. Yi is mole fraction of component in vapor, where here the mole fraction of component in I, that is the partial pressure mole fraction component in liquid, in solution, mole fraction of I in solution, and here it is mole fraction of component in vapor. So combining these laws, mole fraction of component in liquid is the Pi. Pi is equal to Yi x1. Pi is the phase equilibrium constant at specified temperature and pressure. Now, relative volatility. Relative volatility is defined for an ideal mixture as the ratio of the vapor pressure of the more volatile component to the vapor pressure of the less volatile component at the temperature under which fractionation is being accomplished. Alpha, that is the relative volatility, is equal to Y1 x2 upon Y2 x1. Y1 and x1 are the mole fraction of lower boiling component in vapor and liquid, and Y2 and x2 are the mole fraction of component in vapor, feed, in liquid. Y2 and x2 are the mole fraction of higher boiling component vapor and liquid, and this is lower boiling component in vapor and liquid, Y1 and x1. And knowing the concentration of the mole fraction, you can find out the relative volatility. Now, reflux ratio of the amount of material returned as reflux to the ratio of the amount of material going upward. So this TDS is called the reflux ratio. Any fractionation must be performed at the conditions will be those of minimum number of plates at total reflux and a minimum reflux and infinity number of the plates. R minimum is 1 upon alpha minus 1, XCA upon XFA minus alpha XCB upon XFB. XCA and XCB are the mole fraction of A and B in the distillate. XFA and XFB are the mole fraction of A and B in the feed. So we have to find out the mole fraction in the feed as well as in the vapor phase. Speak to me. जाओ पानी पी के आओ, नींद आ रही है. 3 moles of B and 4 moles of C, then the mole fraction of A is 1 upon 8, mole fraction of B is 1 upon 3 upon 8. Like this, you can find out the moles. You find out the residue in the flask. This is the best distillation. The best distillation is non-fractionating, semi-fractionating, and fractionating. अब देखो ये क्या होता है? What's that? Means non-fractionating, semi-fractionating, and fractionating distillation. Non-fractionating distillation. I'll explain what is the difference between the non-fractionating and Thomas.
Yeah.
These vapors, because this part is having the lower temperature than this part. Some of the vapors will condense and will come back to downward and will go to the condenser. And you are receiving these vapors. Correct?
Yes.
This is one theoretical plate. The difference between the non-fractionating, in the non-fractionating distillation, there is no theoretical plate or one theoretical plate. What is theoretical plate? When the liquid vapors rising, theoretical plate. Rise upwards.
Yes.
correct? At this column, and from this column, these vapors will go to the receiver. Some of the vapors will trap from here and will go down to the field. Once again, one more theoretical bit. So there are the number of the stages 1 plus 1, 2. So there are the 2 theoretical bits. This all the best distribution which you will see in the laboratory, because this is the distillation which we are doing for generating the report, crude evaluation report. High vacuum distillation.
So theoretical gate and there is some condensation and gum going as a wave.
Yeah.
So this is 2.
2. Now see the number of the more than 2, that is fractionating distillation. Like this.
Spiral.
This is wire, gas.
Spiral.
Yeah, spiral. And each plate dia is 25 mm, 2.5 centimeter. It is having the 80 number of the holes. 80 number of the holes. Each hole is having the dia 0.25 mm. Then this is a wire and drain. So what happens after condensation? Liquid collects over here, and then liquid come in contact with the vapors coming upward, and then the higher volume component go back down through this drain to the lower side, and these are the number of 30 actual plates. This is a Oldershaw column, and this Oldershaw column you will see in the lab, and this Oldershaw column is 1 meter long. It consists 30 number of the stages and 15 to 16 theoretical stages. It is for the better fractionation, and you can get the component having its actual boiling point during the fractionation. Say you want to separate the normal lactate. Normal lactate is having the boiling point 110, correct? So at temperature 110, you can note down the temperature from here. This is the reflux to maintain the reflux ratio. This is condenser. Vapors rising upwards are coming in contact with the vapors rising upwards. This is the reflux ratio which is being maintained by the this is your solenoid valve. This valve opens for 1 second and remain closed for 10 seconds. So the vapors only for 1 second will go to the condenser. Often from this condenser, these vapors will go to the receiver, or from receiver you will collect the fraction. Up to the 205 degrees centigrade, we distill the crude at room atmospheric pressure. After 205, we connect the whole system through this vacuum pump, and the whole system is running under vacuum. From 40 mm to 20 mm of the HG, we apply the vacuum, and pressure from 40 to 20 mm of HG, we collect the part of the kerosene, means 205 to 370. Part of the kerosene and total diesel we collect at 40 to 20 mm of HG. This whole system is now vacuum. When these are the valve, first you disconnect the vacuum, you open this three-way valve, you stop over here, you disconnect the vacuum, you are measuring the pressure, and this is the solenoid valve which you are maintaining the reflux ratio 1:10 or 10. Okay, so here it opens. It's a magnetic device which rotates like this. When it starts from here, it touches from here. At that time, it opens the solenoid valve, and then it opens the solenoid valve. Then the vapors are going to the condenser, and from condenser to receiver, and receiver to, because the vapors are directly going to the condenser, and after condensation, this reflux head maintains the vapors for 1 second to the receiver and 10 seconds to back into the, for 10 seconds to back to the feed. So this is the reflex ratio. This is a device, correct? This is a device of the to action, and then with the using the formula, because you see the you can calculate the theoretical rate and alpha is relative volatility, earlier discussed. N is the number of theoretical rate, and D1, XD and X0. XD is the mole fraction of normal leptin in the reflex liquid. X0 is the mole fraction of normal leptin in the flask liquid, and so now how you will find out the mole fraction of relative volatility to N-heptane and now this XD and X0, the main thing is this, you have to find out the XD and X0. What you will do, you will do this distillation. You will do this distillation. Okay, in place of this column, you will correct MCH. It's no problem.
This is a standard method.
It's distillate to boiling point distillation. Now, IIP. Then from this here you measure 5 ml, 10 ml, or here you record the temperature. This is the ASTM B86. This is standard method. Either you are getting the data from India or from your Sudan. On both sides, the data will be same because we are reporting at 760 mm of the LG. Vapor pressure, atmospheric pressure is different. Here is 702 or 704. And Sudan might be the vapor pressure 710 or 720. So you convert your observed temperature to AET, Sydney's equation, and the Sydney's equation is this 0.00012. This is in degrees Celsius, 0.00012, 760 minus the pressure of that place. From Dehradun, pressure of Dehradun 704, then 273 plus TC. TC is the observed temperature. So then you will find the corrected temperature in degrees Celsius, corrected temperature in degrees Fahrenheit. This you have to report. In any report or anywhere when you are observing the data, you increase the flame height and then you are getting the final boiling point. This total time of the distillation comes 30 minutes. Okay, this is a manual distillation. And when there is a controversy between the results of the two countries, then only this is the referee method. If the results of two countries by automatic or semi-automatic instruments are coming and they are not matching, then one has to convert using this manual method, so referee method.
I know this is a method for separation. Why
No difference. Means you fill the condenser with ice, and if your temperature, if you are using the kerosene, then you can fill the water at room temperature. If you are doing the
In these tests, in the atmospheric distillation, actually during in the lab,
yeah.
there was a reflux. There will
In the lab,
in the lab during this distillation.
Yeah.
Normally from the distillation tower there is a reflux for each tray.
No, for this distillation there is no reflex.
In the lab there is no reflux.
No reflex, but earlier there was a reflex in that. Now the rate of the feed and the temperature are so adjusted that the volume of the feed is equal to the volume of fraction collected from the head and bottom, and conditions at any given temperature will be constant during the period of distillation. This already I have shown. The batch distillation is our distillation, that is TBP. Definite amount of material is charged to the still part of the bottom and distilled to dryness. Conditions throughout the system are continuous, changing as more volatile distillate taken out and less volatile material moves up the column from plate to plate. Total reflex, I told, operate a batch still on total reflex, that is returned to the system as reflux all the material, condensing as the head without removing any product. So we have then constant condition throughout the system, and now the method can be analyzed like continuous distillation. Open column or unpacked column, less efficient, allows much faster throughput, more easily constructed and simpler to operate. Bubble plate column consists of series of plates over which flows a layer of liquid and reflux flow of liquid and reflux, and through which the rising vapors are made to bubble. The reflux flows from plate to plate through suitable overflow pipes, and the vapor rises through each of the plate in series of counter current to the flow of the liquid. Perforated sieve type developed by Oldershaw for laboratory distillation. The column which I have shown you, that is named as the Oldershaw column, and Oldershaw was the inventor of that column, which is 1 meter long, having the 15 to 16 theoretical plates. Now the Oldershaw, this is the reference of the Oldershaw, 1914 CF, Industrial Engineering Chemistry. Reference is this. Perforated plates are sealed in a tube. Here, this is just all about the Oldershaw column. Are sealed in a tube. Each plate is equipped with a baffle to direct the flow of liquid, a wire to maintain the liquid level on the plate, and a drain pipe to come back the liquid to the feed. Packed column, packing of glass or stainless steel are used in the columns to handle any type of chemical without danger or catalytic action. These are the packing: Pro-Pack, Helix, Stedman, Cannon, and Nick Beer. Now open column, bubble tray column, perforated sieve type column, and packed column. Now this is the objective of distillation for preparation of feed stocks. When we are doing the distillation, we are getting the different feed stocks, and these feed stocks are characterized for their physicochemical characteristics, so that you can decide for what purpose you will use either petrochemical or as fuel. To monitor and control the quality of product, to generate the percent yield data on percent weight and volume, to study the variation of some key properties throughout the distillation range. Data is the basis of property curve which can be used for product optimization to indicate what further processing of heating is required to meet the requirement of a specification, assessing the cost of crude oil for baking key fractions, to generate and use percent property curve for additive property and yield curve for non-additive property. Already I have explained this. Now this is the column. So this column, this is condenser, then this is receiver, here is intermediary, you are taking the sample. Now EFB temperature. This is the EFB temperature which is being used for designing the column. EFB means equilibrium flash vaporization. And EFB exercise is a very exhaust exercise. For generating one temperature data, you need 48 hours. That's why, because to have a full shape of an EFB curve, at least 5 temperatures are required. IBP 10, 30, 50, 70 and 90. Vaporized are required. EFB distillation curves are useful for designing and operation of overhead partial condensers and bottom reboilers, since the EFB temperature represents actual equivalent temperature. In contrast with TBR, the EFB initial temperature of mixture is greater than IBP of ASTM D86, while the FBP from EFB curve is lower. You can see this curve. here. This is the, this is TBP distillation having the lowest IBP and highest LPP. ASTM is having in between EFB and TBP. IBP and in between TBP and AFB, LPP. But EFP is having the highest IBP and lowest LBP, because that all depends on the separation. Correct? So now we come to the why this now. For obtaining EFB cup, sample is heated to a certain temperature and pressure, and is heat test to get the percent.